Okay, welcome back. Happy Monday. Today is May the 2nd. We're covering our last new topic before the test, finding and applying Taylor series. Just to be clear, the material that we are covering today is represented on the test. So make sure that as you are studying, if you're studying in order, you give yourself time to do this last section and practice with it. It's on the test. Project number 8 is due right now, so throw it in the folders. If it's not done, get it to me as soon as possible, but it's late if it's not in the folder right now. Coming up on Wednesday, we have our review day for test number 3. I don't have any agenda for Wednesday. You're just going to do problems. At the start of Wednesday's class, I think we're going to spend about 10 minutes just kind of watching a cool video, doing some stuff with series. But if you're not into the video, you'll just put your head down and do problems the whole time, okay? And then our test is coming up on Friday. The test is on everything since the second test. So you're going back to all the stuff we've done in chapters 9 and 10. Just looking ahead, we've got after the test, 3 more days of new material, all about differential equations. Then we've got a review day for the final exam, and our final exam is May 18, which is 2 weeks from this coming Wednesday. Questions on the calendar? Great. So here at the top of page 60, today we explore Taylor series further. The process we've seen for getting Taylor series is cumbersome. Today we'll explore some alternatives. So suppose that we wanted to, here number 1, find the Taylor series and the interval of convergence for ln of 1 minus 2x. So the standard way for us to do this problem is to start taking a bunch of derivatives of ln of 1 minus 2x. And then plug in, x equals 0. It wasn't specified here, but I think that's the idea. Plug in our value for a into all of the derivatives, and then use that big formula with all the factorials and all the powers. Yes? As an alternative to that, we're going to take advantage of the fact that we proved this last class. ln of 1 plus x has that Taylor series. We did it together last class. And all we need to do is say, hey, well, what value of x can I substitute so that I get ln of 1 minus 2x right in here? Not just -2, but change x to what? -2x. That'll do it. If you change this x into a -2x, it just becomes 1 minus 2x, which is exactly what we want. So we are building the thing we want using the thing we already have. And hey, I've got this formula for ln of 1 plus x, and I can change all of those x's into -2x. It's pretty easy. So let's give it a shot. So ln of 1, I'll write it as 1 plus -2x just to really tie it into that ln of 1 plus x formula. And then all we're going to do is change every one of these x's in the big long formula into a -2x. So the first x becomes -2x. Next up, minus -2x squared over 2. Plus -2x cubed over 3. Do one more term here. Minus -2x to the 4 over 4. Everybody good? Just change the x's to -2x's. Okay, and there's a little bit of cleaning up that I guess we should do. So let's do some cleaning up here. I'm going to come down here, but we're not yet answering question 2. So we go -2x. Then this -2 is going to get squared and become +4, but there's still a minus sign in the front, so I think it's a negative. And I'm just going to write, instead of 4, I'm going to write 2 squared times x over 2. X squared. Let's try the next guy. You could reduce, but I'm not going to. The next guy is -2 cubed. That's going to be a negative thing when all is said and done. There's a plus sign in the front, so the final sign there is negative, yes. And the 2 is cubed, and the x is cubed, and there's a 3 on the bottom. Where? Oh, I'm not doing problem 2 yet. That's a different problem. I just ran out of space. Okay, last one here. Negative 2 to the 4 with a negative sign in the front. Is that positive or negative? Negative. Okay, so it's going to be 2 to the 4, x to the 4 over 4. So just by writing it out, we start to see some patterns that maybe weren't apparent in the beginning. First of all, every term is negative. It kind of looked like an alternating thing at the beginning, but it's not. Every term is negative. And then by avoiding reducing, you know, like 2 to the 4 over 4 reduces, but if you don't reduce, then you get to see the pattern here. And so with the pattern, we're in a position to find the general term. So looks like I've got a subtraction in front, 2 to the, what letter are we typically using? We'll put an n up there. What's the power on the x? Also n, because of the 4, 4 is the same and the 3, 3 is the same, divided by n. Perfect. There's the general term. Cross that one? Oh yeah, I haven't. Yeah, we're not doing 2 yet. Okay, so that right there is the Taylor series. I think it's clear that it was easier to do this than to start from scratch and calculate a bunch of derivatives and do all the factorial stuff and all the canceling. That's the point. Okay, and then the interval of convergence. Okay, so you just handed in a project full of problems where you found the interval of convergence. How did you do that before? What test? Ratio test, right? Probably on every one of the problems in the project, we did the ratio test, although some of us found that one of them was a geometric series, which was fancy, but typically we would do the ratio test. So you could do the ratio test. Hey, we did the work. We found the general term. You could do the ratio test right there, but there's an easier way. Does anybody happen to remember the interval of convergence for this series? And actually, this is a good time for us to take a look at a new reference sheet. I think it's page 3. Can we go almost all the way to the beginning of the packet? And at the bottom of page 3, sorry, it's not labeled page 3, it's labeled page 1. It's the second piece of paper, but it's called page 1. At the bottom, you guys see 5 famous Taylor series? Yes? Right, okay, and the very last one is ln of 1 plus x. It's the one we're playing with now. This is also a reference sheet that you'll have with you on the test. Okay, so what was the interval of convergence here? -1 to 1. I'm going to write it this way. X was trapped between -1 and 1. Equals on which side? The right side. Okay, so that's the interval of convergence. We proved that last class as well. So what did we do? Well, all we did was take that known Taylor series and we changed it into the one that we were interested in by replacing x with -2x, right? Thoughts on how we can find the interval of convergence of our series easily? Change the x into -2x. So let's do that. -2x is trapped between -1 and 1, inclusive on the same side it was inclusive on before. Divide all 3 sides by -2. So it goes 1/2, x in the middle, -1/2. What about the inequality signs? They flip, right? So this becomes a greater and the last one becomes a greater than or equal to. When you multiply or divide an inequality by negative, changes the direction. Questions on taking the original interval of convergence and finding the new interval of convergence? Same substitution that we did before. Did I do this right or wrong? Keith, am I right?
I'm just confused that you like switch the sign and then you switch the thing too, the symbol.
What did I switch? I divided everything by -2. Right, so that, yeah, so this guy became the +1/2. This guy divided by -2 is -1/2. No, when you multiply or divide an inequality by a negative, you have to change it. I mean, think about it. If you kept it the same way, then it would say x is bigger than a half and simultaneously less than negative a half, but that's not okay. All right. So again, hoping that you buy into the fact that that if you can use an existing Taylor series to build a new one, it's easier than starting from scratch with a million derivatives and all the factorials. And it's also easier to avoid the ratio test and then do the endpoints, right? All the stuff that we did in the project has been avoided by using a Taylor series we already know. Okay. Now, finally, we'll do here number 2. You can multiply or divide in the way that you might expect. If you want the Taylor series for x squared ln of 1 minus 2x, what are we going to do with this current Taylor series that we have? Yeah, so we're just going to take the existing one, the most recent one, and multiply everything by x squared. That's all. So x, different color. Yeah, this is now number 2. So I'll start by writing this so that we know it's number 2. So x squared ln of 1 minus 2x equals so all we're doing is multiplying everything in this bottom black thing by negative 2x cubed is good. Next one. 4 is good. Divide by 2. Just write out 2 more terms if you can. Just multiplying everything by x squared. So the next one is 2 cubed x to the 5th over 3. 2 to the 4 x to the 6th over 4. And let's show off and actually do the general one as well. So everybody's getting multiplied by x squared. 2 to the, and that's the same, x to the, not quite, and plus 2. Okay. 2 more x's divided by n. Fantastic. We're not going to find the interval of convergence here. Oftentimes it stays the same, but that's not as predictable. I'm happy with what we got. Questions on that one? No, it's the same as, it's the 1/2 to the negative 1/2, as just like it was before. You could multiply the general term by x squared as long as you've got it in sigma notation. Yeah, that's fine. No, not risky. Okay. We didn't have to, no, it didn't say sigma notation. If we did, we could have just done the general term. Yeah. Okay, so pencils down. I'm going to do some stuff here, and you guys are not going to write it down. So we're going to derive in number 3 a formula for e to the I theta, which leads to the absolute most awesomest of equations in all of mathematics. So let's see if we can get there. Okay, so e to the I theta. So first thing I want to do is, what do I want to do? I want to remind us of some things. Can you guys go to that same reference sheet we just looked at and recognize that on that list down there at the bottom, the 5 famous Taylor series, you have one for sine of x, yes? It starts x and then minus, not quite. Right, were you looking at cosine maybe? Yeah, okay, plus x to the 5th over 5 factorial minus da da da. So just a fact, we're going to have it up there for reference later. While we're here on that page, let's write the one for cosine of x. What's the first term for cosine? 1. So all that I know about the sine, like I've got these things, those 2 memorized here, but all that I have to remember is the first term, because then it's just skipping over powers and alternating signs. So the next term skips the x term and jumps to the x squared term. And then the next one skips x cubed and jumps to x to the 4. Okay. And the last one, the one that we're actually going to really start with, is the one for e to the x, which is also there. What is this guy? No. Okay, I think this is enough terms, but if we need more, we know where to find them. Okay, so 3 things that we've already seen in this class, and even if we don't remember how to, even if we don't recognize them or have them memorized, we could get there by doing the derivatives and plugging in and doing the factorials. This is what we would get. Okay, what I'm interested in this problem is this very strange looking thing up here, e to the I theta, where I is the imaginary square root of -1, right? This is pretty much the only time we're going to talk about I in this entire semester. Calculus exists in the complex plane, but Calc 1 and Calc 2 and Calc 3 is the calculus of real numbers. So we just don't talk about it here. But we'll talk about it for today. And let's see if we can't use this e to the x formula to get an alternative for that e to the I theta. What does it even mean to take e, this real number, right, 2.7 and change, and raise it to an imaginary exponent, raising it to e to the I? What does that mean? E to the 2i, what does that mean? Well, the formula that we've got here, we've only been playing with real numbers. And so in theory, for our understanding, that formula is only good when x is a real number. But it turns out the formula generalizes, and it's exactly the same formula when you plug imaginary numbers in here. So you just have to trust me that it works, but we're just going to substitute. Instead of x, what are we going to put? I theta, right? That will give us a starting place for that e to the I theta. So e to the I theta equals, copy this thing, but all of the x's become I thetas. So far, so good. Okay, so next thing we're going to do is actually start squaring and cubing these things out here. So 1 plus, sorry, I'm just going to copy that guy, I theta. Okay, the next one is an I squared and a theta squared. What is I squared? It's -1. I squared is -1. So this guy's going to become minus negative, so -1, and then theta squared over 2 factorial. Next one is going to be an I cubed theta cubed. What is I cubed? I'll put this over here. We've got I squared, we said was -1. I cubed is just multiply the previous guy by I. And then I to the 4th is back around to +1. And then we loop to the front of that list. Okay, so I cubed, we said, is -I. So we'll go -I theta cubed over 3 factorial. Next one is I to the 4 theta to the 4. I to the 4 is 1, so I'm not going to write that guy. I'll just put plus here, theta to the 4 over 4 factorial. Let's do one more term here. The next one would be I to the 5th, which is back around to the beginning of the list. It's just I. So plus I. Theta is going to have a 5 on it, 5 factorial there, etc. Okay. Next thing we're going to do is just some grouping. We are going to pull out to the front here all the things with no i's in them. No i's in them. So the first term I see is a 1. Great. The next one has an I. I'm not going to write it yet. The next one has no I. So minus theta squared over 2 factorial. What's the next one with no I? Plus theta to the 4 over 4 factorial, right? We didn't write it, but maybe one more term. Minus theta to the 6 over 6 factorial. Yeah? Plus dot, dot, dot. I'm going to put this in parentheses, although it's not mandatory. Plus, now every term we haven't written yet has what in it? I. I'm going to pull that I to the front by factoring it out of big parentheses. So everybody that had an I in it, oh, we've already got the I in the front. So the first term is theta. That one's got no i's. That one has an I, which we pull in the front. And what's left? Negative theta cubed over 3 factorial. Next one. Theta to the 5th over 5 factorial. 1, 2, 3. Let's do one more. What's the next one? And that one's minus, right? Minus theta 7 over 7 factorial plus dot, dot, dot. Okay, so that's just reordering, regrouping. Now this guy in the first set of parentheses, Should look an awful lot like one of our 5 famous Taylor series down there. What does that look like? Looks like cosine, but it's not cosine of x, it's cosine of theta. Wonderful. So this guy right here is cosine of theta. And the other guy is really sine of theta with an I in the front. Okay, so that means, so putting it all together here, let's squeeze this in the bottom. We started this whole calculation with an e to the I theta, right? Equals, equals, equals. So now in a much more compressed form, this is really cosine of theta plus I sine theta. And so this is a way to get our hands on what it might possibly mean to take e and raise it to I times something. E to an imaginary number. Okay, no problem. We're just gonna take a look at the number sitting next to the I. It's called theta here. We're gonna find cosine of that thing. We'll just think of it as an angle. We'll find cosine of the thing, we'll find sine of the thing, we'll put an I right next to the sine, and that's it. That's what it means to take e and raise it to some imaginary number. Okay, so that equation is pretty cool. What does that mean?
The way I saw it, I thought that when you squared it up, we were going to be getting rid of the I, but
yeah, they went away for the evens.
Is there a way on the cosine theta plus I times theta will that I work out the math so that you can graph it or something?
It is possible to graph complex numbers for, and it might be something you've done in a pre-calc class where the real axis is like the x-axis and the imaginary axis is the y-axis. So for sure you can plot, cosine of theta as some number going to the right, and then I sine of theta, you just go up. You ignore the I, you just go up, and so you've got some point over here. You guys do this in pre-calc stuff? Maybe, did you talk about like polar coordinates and like graphing, like rotating? Yeah. Yeah, so I think back in pre-calc, if you go back, if you still have your notes, you'd see that you plotted things like that. Yeah. Okay, so this equation right here in the box is true for any value of theta you wish. We're going kind of crazy here with the numbers. E is a real famous number, I is a real famous number. How about we plug in another famous number? Let's plug pi in for that theta. Yeah, so the left-hand side becomes e to the I times pi, right? Equals, so just copying my formula, cosine of pi plus I sine of pi. Great. So that means that e to the I pi equals, cosine of pi is -1 plus I times sine of pi, 0. So that means that e to the I pi is -1. Right. Which is just mind-blowing.
Are we still talking about the Taylor series of it, or are we just talking about
just numbers? These are just numbers we're playing with here. If you, I think the calculator can handle this. I think. E to the, there is an I on your calculator. It's down here in yellow. E to the I pi. What are we hoping? So even if you didn't believe anything that I said, now that you believe it, the calculator says it's -1, right? Yeah, so I like this version of the equation. This is my favorite equation in all of math. You might have your own top 10 list, which we can discuss some night, but that's my favorite. Now some people prefer adding 1 to this equation, adding 1 to both sides, so it becomes this. Equals 0, right? And it's just an alternate version of the same thing. And so some people really like that because that means that it involves e and I and pi, really famous numbers individually. And then 1 is great because 1 times anything is itself, right? So what's the fancy name for 1? Because it doesn't change when you multiply. It's like a it's a 2-word phrase. What is it? It's the multiplicative identity, right? Because it doesn't change, and identity is just a 1, doesn't change the thing. And 0 is great because 0 plus anything is the anything. So what is 0 called? The additive identity, right? Identity element for addition. And so it's like you've got 5 of the most famous numbers all in one equation, but that seems kind of artificial to me, personally. Yeah. 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 You guys know tau? What is tau?
I had to use it. I don't know what it really is.
Tau is just 2 pi. Yeah. And using tau makes a lot of things a lot more reasonable when you're talking about trig stuff. Yeah, Sam. Is what hard coded in? So I don't think that that's I don't think that that's coded in, because I could do, for example, oops, second that guy. So like I could I could type in some crazy nonsense. Like that is definitely not hard coded in, right? But what do you think it did? How do you think I could get this? Here, look, I'll scroll over. It's got a sum and then an I tacked on the end. What does that remind you of? See it? There's a, right? So what would I type on my calculator here? If I wanted to get this 0.30 number on the calculator? Cosine of 1 point, I'll leave it to me to type some stupid thing here, 431. I think this is hard coded into the calculator, is the thing in the box. Yeah. All right. On the next page, we will start with the activity. When you get to part C, I expect a lot of tables will get stuck. We'll get you unstuck. It's straightforward once you know what you're doing. We'll walk around.